Okay, so we've been spending a lot of time in this unit talking about how we're going to describe data, the different ways to graph, and then once it's graphed, how do we really analyze it, right? We've talked about SOX, and part of SOX, if we remember, was the last two in the original way we talked about it were center and spread. So I'm going to take a few minutes here and just kind of go a little bit deeper into what are these centers and spreads, and what are some of the terminologies that are going to be associated with them. So the first thing, go back and remind ourselves measures of center. So the first thing, you got a median, which was the exact middle set of the data, middle of a set of data, excuse me, versus the mean, which was the average, where we add them all up, divide by how many observations there were. A great way to think about the mean is a balancing point for the data. If we think about it in terms of a balancing point for the data, it's going to help us as we start talking about one of the terminologies. So again, you've seen this before. Remember, we've called this X bar, and then we sum the observations, divide by the total number of observations. This is not new. You've been doing this for a long time. A lot of you, when we started doing this in class, started finding the average this way before we ended up discovering this one var stats, which automatically did X bar for us. So remember, X bar is the mean. So going back, if you'll allow me to, this idea of a balancing point, that's going to be crucial for this term that we're going to throw out right here, which is the term resistant. And a resistant measure is something that is not easily influenced by extreme observations, aka outliers. Right? So we think about this for a minute. Is the median resistance. So let's say we have the data set 2, 3, 3, 4. Well, the median here would be right between the 3, so it'd be 3. All right, there's the median. The median is 3. The average, 5 plus 8 plus 5 to 8, 12 divided by 4, the mean, the X bar, is also 3. So if all of a sudden we threw in an extreme observation, let's throw in something like 80. Well, we can see here the median, right, the center of the data is still 3. But you guys are sharp enough with your math to realize, wait a minute, this X bar is going to go up quite a bit. So this extreme observation hasn't affected the median. So is it resistant? Yes. But the mean with this 80 is going to get pulled up a lot higher than 3. Whatever that might be, 5, 8 plus another 4, 12, or 92 divided by 5. So it's somewhere, close to 19. So we've definitely made a big change by this extreme observation. So is the mean resistant? That answer is no. One of the things to realize is sometimes when people are reporting the mean or the median, they can both be used by news folks, people in radio, on your nightly news, in newspapers, writing articles. Sometimes they'll use the term average, and sometimes it means mean, sometimes it means median. And at times maybe that's them trying to be a little bit deceitful maybe with the word, because sometimes it makes more sense to report the mean instead of the median. Sometimes it makes more sense to throw out the median instead of the mean. And I'll show you why in just a minute. If you think about it, a couple things that you hear a lot about, average job salary or average home price. So why would maybe somebody decide that they'd like to report the mean instead of the median? Why would they go for the median instead of the mean when they're claiming these? And I'm going to put averages here because that term gets used loosely sometimes in day-to-day. As you guys are out there consuming all this data, let's start thinking about, well, what is it we're really looking at? So here's the idea. Let's say that we have a data set that's heavily skewed to the right, or maybe we have some kind of data set that's skewed to the left, right? So we take a look here. Now, we got a few observations that are kind of pulling that tail. We start thinking through this, right? We've already kind of thrown out this idea that the median is going to stay somewhere in the middle, right? If we count it down from both sides, it's going to be at the halfway point. But with these extreme observations, we can see in the previous kind of numbers that I threw out there, that 80 really pulls the mean up. So when all of a sudden you're looking at extreme observations, this one right here is going to end up pulling the mean out away from the median. These observations down here will end up pulling this mean down quite a bit. So why would somebody maybe want to report the mean over the median? Well, let's say that this particular set of data is a company and it's their salaries. Well, maybe this is the CEO of the company that's making a whole lot of money. Well, to make the company look better, they might say, hey, our average salary, right, is a lot higher than maybe it really is because of this one outlier. So they would maybe want to report the mean to make themselves look better. Maybe somebody that's trying to shed a negative light on that company would actually go back and use the median and say, well, let's use something that isn't as affected by that extreme outlier. Maybe over here are some test scores, right? Maybe this is data on test scores. So here, if somebody's trying to make their school system look really, really good, they'd probably want to lean toward using the median because it's not really being affected by the few low scores down at the tail end of this data set, right? So they would probably report our median test scores were so-and-so, making them look better. Maybe if somebody's out to get that group of people, then they would also say, well, actually, your average test score is a little bit lower, right? Because, again, the median not affected by the outliers as much as the mean can be and is. And a lot of that comes back to, you think about the formula where you sum all those observations up, you have to divide by n. Well, when we get big observations in the top, it's going to really, really affect the outcome of x bar versus the median. There actually isn't a formula for it. You literally just count from the outsides in. So there's kind of a look at why somebody might want to, when use the mean or the median, kind of to tell their story the way they want to do it. So a great word here is trying to figure out what's the most appropriate measure of center. Appropriate. Make sure I get the R in there. So at times the mean is more appropriate than the median, or the median might be more appropriate than the mean if we have heavily skewed data sets, and depending on what we're trying to say. If a data set's symmetric, it's really not going to be a big deal, right? The median is going to be right there halfway through the data, and the mean is going to be right there with it. But typically in a symmetric distribution, the mean and the median are very, very closely, so either one is, using that term, appropriate. Now, we'll go back and look at the measure of spread, the last part of SOX, a little more in depth. IQR, it's a range between Q1 and Q3. The range, these are things that you're pretty familiar with, but I'm going to take a few minutes here. Let's look more into the standard deviation. And we've talked about it before. It's the average distance from the average. So let's, again, we'll first break it down with deviation. How much something deviates, how much does it change from the mean? In other words, we take these observations and we subtract the mean, right? The distance or the difference from the mean. So let's say that we had this situation. 4 people complete some task. It took them 1 minute, 3 minutes, 7 minutes, 9 minutes. So the average of that, or the actual mean, 1 plus 3 plus 7 plus 9 divided by 4 is 5. So breaking down each one of those things deviations, well, 1 is 4 below, so that's negative 4. 3 is 2 below, so on and so forth, right? 9 is 4 minutes above the mean. If we were to try to take the average right now, and we were to sum these things up, negative 4 plus negative 2 plus 2 plus 4, we'd end up with 0 over 4. Well, that's not going to tell me anything. Standard deviation of 0. That doesn't make sense. So what we're going to do is play a little bit of a math trick. And we're going to turn this standard deviation into something called variance. And really all variance does is we're going to square our deviations. So the notation is going to look kind of crazy initially, right? Here's all the deviations. We're squaring them. There's summing them up. And then really what we're doing is we're dividing by, this is where it's a little bit tricky, and you're going to have to go with me. We're dividing by n minus 1, not n. Now, earlier in the class period, or earlier in the course, we've seen that s of x and sigma of x have been slightly different numbers, right? Maybe this one was 2.3 and this one was 2.5 something. And some of you have asked, well, why are those different? This is why. To actually find standard deviation, we divide by n minus 1. And the best reason I'm going to give you right now in this video is because that's the way it is. If you like more detail, we can talk about it somewhere else. But without getting too complicated, without trying to overwhelm a lot of you with this, here's the idea. Here are the deviations that we saw on the previous page. Square them. Negative 4 squared is 16. Negative 2 squared, 4. 2 squared, 4. 4 squared, 16. Now we're going to add these up. We're going to average those deviations squared, or we're going to average the variance. So again, 16 plus 4 plus 4 plus 16 is going to add up to 40, and we're going to end up dividing by n minus 1, so we're going to divide by 3. Then we end up with 13.33. Now, what are the original units of data? We're talking about minutes that it took to complete a task. So variance, we squared everything, so we end up with minutes squared. And the question becomes, well, what does that mean? What is a minute squared? And the answer is nothing. So right now we've got this idea of variance equals 13.33. We can't really use it. We'd like to get it back to a unit that we can, right? We want to get back to the units of the original data, like this is saying. So what do we do with 13.33? We're going to turn it back into our standard deviation by taking the square root. So basically, the idea here, we had our deviations, but if we sum them all together, it will always be 0. So we play a math trick, we square them, then take the average, and then come back. So we're going to go, right, you want to think about it this way. We got this information, we're going to square it, and then we're going to take that and come back and take the square root of it, right, of the data to get back to our right units. So that's where you're getting your data, how much is varying from the mean on average. We're going to kind of play this trick where we square it to make it all positive, find the average, and then take the square root to get back to the right units. You guys are never going to have to do that by hand, just as a heads up. I just wanted you to see where it's coming from, right? Standard deviation is only appropriate if the mean is chosen as a measure of center. And the question is, well, when would you not use the mean? And that goes back to this idea of resistant. Right? If our data is heavily skewed, maybe standard deviation isn't appropriate. We can always calculate it, but it might not be, here's this word again, appropriate to use. So when would standard deviation be 0? Well, let's think about this. How would you get nothing to be different? How would you get the average distance from the average to be 0? A great way to think about that. If all the observations are the same, think about if you had 5, 5, 5, right? The average there is 5, and everything is 0 from 5. So there's one way to kind of, if that's making sense to you, you got a good feel for what standard deviation is. So the question now becomes, is it resistant? So since we're using the mean, right, you go back, you think about, we're getting the average distance from the average. Well, the mean isn't resistant, which means standard deviation is also not resistant. No, it's not resistant. So now let's think about it. Well, what were our measures of spread, and which ones are likely to be affected by extreme values? So we just saw the standard deviation. We actually use the mean, right? It uses X bar. So not resistant, right? Think about the range. The range is max minus min. Well, if there's an extreme observation, likely it's going to be one of these two things. So again, not resistant. And the other one that we do know, the IQR, well, you think about it, if there's an extreme observation, will that really affect the quartiles? And here the quartiles, again, are just medians, right? Q1 and Q3, we can think about them. They're medians, and we've seen it before. The median is actually resistant. So the IQR is actually a resistant measure of spread.